multivariate calculus.
Sorry?
I hope you had time to go through higher order differentials where you're differentiating the function several times. Did you follow those sessions I shared with you?
I followed some.
Okay.
Yes.
But for others, you have not managed.
Others, no, not yet. But I think
Okay.
I plan on doing that this evening.
Okay, that's fine. Let's just proceed. We are still looking at unconstrained optimization. And I recorded to us that unconstrained optimization simply means there is no constraint, right? There is actually no constraint, no limitation whatsoever. So we assume that we are free to go as higher as we can. We can go as low as we can without any constraint. Now, we indicated to us that the function that you're trying to minimize or maximize is called an objective function, yeah?
Yes.
We say that function is actually called an objective function. And from that, we also did record to us that the objective function shall need to be differentiated once. After differentiating it, set the derivatives equal to 0, yeah? And then solve for the critical value, isn't it? Solve for the values of x. And once you're done doing all that, we recorded to us that the next thing that you need to do is to do the second partial, right? Like derive it for the second time. And then you got to substitute those critical values, check if, the second derivative is greater than 0. If it is greater than 0, you have the minimum. If it's less than 0, you have a maximum. Something like that.
Yes.
So even what we are having this afternoon is almost related, only that the conversation has been lifted up in terms of the notes. We are having what we call multiple augmented functions. The multiple augment functions, they have on the right-hand side more than one variables. In other words, the independent variables are many. You're not just dealing with only one, as we saw previously. So this time around, you have many values of, the independent variables. You could have a function, let's say y is equal to maybe 3xy plus 2 y squared plus 3z, right? You've seen there how many variables on the right-hand side. We have 1, 2, 3 different variables, x, y, z, right? Yeah, you could even have another one, maybe let's say 5w, yeah? So now how do you differentiate such a function? That's a word, that's a question. How do you differentiate such a function? Okay. When you're given such functions, then you need to learn that you cannot use only, the direct derivatives. Instead, you have to do what we call partial derivatives. That is to say, you shall differentiate this particular function with respect to each variable, okay? You start with the first variable, the second one, and the other, okay? So now our variables are not x, y, z, just labeled x1, x2, x3, x4, just like that. So in our case, we just have two variables, x1 and x2, yeah? So we can derive this function with respect to x1, and what we are going to find is called a partial derivative. So say dy dx1, meaning we are deriving this entire function with respect to x1. In other words, we are fixing our eyes where there is the x1. Where there is no x1, that shall be treated as a constant, right? That shall be treated as a constant. And for that reason, you will not do what? You will not drive it. It will be a 0 for you, okay? So 400 is treated
As a
as a
constant.
0. That's what we said. So have here, we shall have negative 6x1, right? Because you drop the, you remember the conversation, drop the power,
Yeah,
you
yeah,
know,
yeah.
yeah. We cannot repeat this thing. This will be just negative 4, right? Because this x1 is raised to the power 1. And when we come here, this 2x1, x2 can still be written as 2x2, x1. You know that that's the same thing, eh? Because multiplication is commutative. That is to say, 3 times 2 is same as 2 times 3. It doesn't
Mm-hmm.
matter. Yes, so this is what I've just done. Writing on the same, you will treat this as a coefficient, the whole lot of it. Okay, this and the other variables that are not x1, it will be just treated as a constant, as a coefficient. It will be just as good as you say this is just a 2, right? 2x1. That's what you mean. Okay.
Lisa, repeat what you have said on the second, because
Okay.
my thinking.
Mm-hmm. What
Yeah,
was your
kindly
thing?
repeat on on the driving with respect to x2.
Oh, so I was saying we are focusing on x1, right? Because we're driving the entire function with x1. So
Mm-hmm.
everything that is here, 2 and x2 shall just be treated as a coefficient, like as just as a coefficient. That's all. You get what I mean, eh? Just a,
Oh,
Mhm.
I get,
You just
I
treat
get.
them, hold them as coefficient. So this is
Mm,
x1 to the power 1.
okay.
Drop the
No.
power, it will be 1 multiplied by 2x2
X, yeah.
times the x1, 1 minus 1, which will be 0. So you shall have plus 2x2. You get what I mean, eh?
Yeah. Not the one that is written here in the book, which is 2x1, right? No.
Yeah, no, it's
That one is
2x2.
incorrect. Yeah. That's where
No,
I got confused.
it is still
I just,
2x2.
no. Oh, oh, I'm confusing with the third one, I think. Where,
Oh,
where,
yeah.
where?
Mhm. Okay. So
Oh,
so you're following, eh?
no.
Then
I,
mhm.
Hmm, I'm a little bit confused here.
We are driving this function. The function is this one.
Yes. Yes. So, okay,
Mhm,
let me just explain my thinking. Yeah, we are
mhm.
deriving with respect to x1, right? So when
That's
we
right.
derive, yes, when we derive x1, 400 is 0, and then when we multiply, we'll have negative 6x, 1 minus 4.
Mhm.
Yes. Now the plus. Why are
Yes.
we getting to 2x? Why are we getting to x2 instead of because these are treated as a whole, like the 2x1, 2x are treated as a whole. So when we are
Yeah, it's one
deriving
number.
with respect to x1, we are remaining with 2x2.
Mhm.
Okay.
Because x1 will disappear. It is raised to the power 1. That's why I told you that this can still be written as 2x2 x1 so that you can easily use your rule. This should be treated as a coefficient. That's what I said. Drop the
Mm.
power 1 times this coefficient, 2x2, and x to the power 1 minus 1. Like that, this will become 1, and you just have 2x2.
No,
You got it?
it's understood. Yes.
Okay. Then
Mm-hmm.
when we come to negative 5x2, that one doesn't have x1. So all these will be treated as constants,
Mm-hmm.
zeros. Okay? This is what
Mm-hmm.
we call the partial derivative with respect to x1. It's a partial derivative of x1. And you set it equal to 0. Since we said the first derivative should be set equal to 0, yeah?
Okay.
Like the way how we are doing there, when you differentiate once, the first derivative is set equal to 0 so that you can solve for
You
the
can
critical
solve for
value.
x. Yes.
That's what you're doing. This is the first derivative. Set it equal to 0. Okay. Now we can go on to derive this with respect to x2. You get it, eh? This, and that, they'll become zeros. They don't have x2, right? Then you have 2x1 now. You get what I mean? Because it will be 2x1, x2 to the power 1. This will be treated as a constant. Remember what I said? As a coefficient. So, when you come here, this will be negative 10, right? Negative 10 x2 plus 48. Because this x2 is raised to the power 1. You can think through. You got it?
I'm a little bit confused.
Okay. No, but are you fine with the first one?
Yes, with the first
Okay.
one, I'm okay, which is where we differentiated 6x1 minus 4 plus 2x2. This, I mean 2x2, yes. Then the second, we drive to the, with respect to x2, we are having, with respect to
It's
x, we are
0
having
here.
2x1, positive 2x1 minus 10x, is it?
2. 10x2
Yeah, 10x2, which
plus
is
48.
plus 48. Oh, yeah, 10x2 plus 48, we equate it to 0. So we are now differentiating further, right?
Now we have differentiated with respect to x2. Let's move step by step. So this one and this one, you agree that these are zeros, right?
Yes.
And when you get here, since this is x, you are differentiating with respect to x2, then x2 will disappear, you just remain with the x1, right?
Yes.
Then you have negative 10 x2 plus 48. We're good up to here, equal to 0.
Yes.
These are second partials, meaning this is a partial derivative with respect to x2 now.
Yes.
This is important. We use more of this in microeconomics. Yeah. So now, which means that if you had another variable, let's say maybe x2, x3, even x4, you could have continued like that until you are going to have 4 partial derivatives. Okay. Did you get it?
Baby, hello. Hey.
Hi. You got it?
Okay. I'm back. Just hold on one minute. I'm in class. I'll call you. Right. Hello. Yes, sir. Sorry.
Okay. Hi. No, it's fine. So I was saying, if you had the 4 variables, you are going to have 4 partial derivatives.
Yeah.
Yeah. 5 variables, 5 partial derivatives. And what is our next step? You set these equal to 0 and solve for what?
for
x.
x.
So now you can have these as spontaneous equations. See x1
Mhm.
plus 2x, you collect like
Mhm.
terms together. It will be equal to positive 4. 2x1
Mhm.
minus 10x2 is equal to negative 48. Right?
Mhm.
You've seen that?
Mhm. Yes, sir.
Then you can solve. You can solve this spontaneous equation. You remember in high school we were learning how to solve spontaneous equations.
Mhm.
Right? There are many methods that you could use solving a spontaneous equation. You learned that you can use the elimination method.
Mhm.
You can also use substitution method. What else can you use? You can even use what? You can use the Cramer's rule method. You
Mhm.
know the Cramer's rule method, that one where you use matrices.
Yeah.
Mm, yeah, you can even use the Gaussian elimination method. You can use the reduced echelon. There are just many methods, but they all give you the same answer.
Mhm.
Okay, for the purposes of this conversation, I'll use the substitution method. We can pick the first equation and make 2x the subject of the formula. So it
Mhm.
will be 2x2 equals to 4 plus 6x1, right? We divide it through by 2 so that we can have x2 the subject of the formula, isn't it?
Mhm.
2 plus 3x1. So this is the x2. So which means we'll go into the
Mhm.
second function where there is x2, we put this, right? So we shall have 2x1, right? Minus 10,
Mhm.
open the bracket. X2 is what? 2 plus 3x1. All that is equal to negative 48. Have you followed up there? Hello?
Yes.
Yeah, you can use
Hello, sir.
any method of your choice. The
Mhm.
key message is that we are solving these functions spontaneous. That's my take home message. Okay. So
Mhm.
when we solve, we can expand. Right. Are we able to FOIL? Yes. 10 times 2 of negative 20, yeah?
Mhm.
Negative 10 times 3, negative 30, x1 equals to negative 48. Mm.
Mhm.
This will give us 2x1 minus 30x1, it will be negative 28 x1, right?
Mhm.
Got to negative 48 plus 20, isn't it? We got
Mhm.
the 20 across the equal sign.
Mhm.
Mm. So that other one will be negative 28, right? Even this will be negative 28 this side. Negative 28 is equal to negative 28 x1. Since we just want x1, divide through by negative 28x both sides. X1 is equal to what? 1, right?
Mhm.
You're fine?
Yes.
And it's easy to find x2 if you have found x1, right? Because you can use the any of the equation,
Mhm.
okay? Any of the equations to find x2. So that x2 can be equal to 2 plus 3 times x1 is 1, and the x2 is equal to what? Is equal to 5. And we end there like that. Mm-hmm. You got it?
Yes. Just a minute.
Okay. So x1 and x2 is equal to 5. That's that.
Nakilasange fyaba wrong.
Hmm?
Nawe fya nakilasanga fya wrong.
Oh, you use the other method.
The answer is very wrong.
Maybe you use the simultaneous equation. It should give you the same answer if you've done the right thing.
Maybe I've done it the wrong way.
The
So,
partial. If you get calculus, we will finish early micro. Because I'll just be telling you that here you have to differentiate. Here you have to simplify. Then if you don't know how to differentiate, you'll be like, because there you have very complicated functions, right? Some functions, they look somehow. Especially you'll be dealing. I talked a bit about the Cobb-Douglas function in one of the recordings for higher order differentials. Please, you need that one.
the
For
one that
Cobb-Douglas
has the lambda, the
alphas,
shiny, the
the one that has got alphas and betas.
I didn't get it. But
No,
I
maybe
think
you're just in a hurry.
yeah,
Yeah,
I'll
you need
go
to put
through.
that. Mm. That
I'll
one
go through.
is That one comes a lot when we are dealing with the compensated demand functions and compensated demand functions, Hickshian, and Marshallian demand functions, Hickshian demand and Marshallian one, including the Chambalian demand functions. Those are very advanced functions, and you need to use the advanced calculus to handle them. Please, you should be conversant with those, the Cobb-Douglas functions. They are used most
Noted.
of the time, and also the Lagrangian, the Lagrangian multiplier. It's a big conversation in economics. Okay, so that's what is there. In short, solve the functions spontaneously. I think you've created solve, find the values of x. So you find the values of x. Okay. Now that you have found the values of x, our question is to find out, do we have a relative maximum or minimum? All right. Because now we have found the two functions, right? You have two functions. You have two critical values, x1 and x2. We don't know whether the function at x1 is a maximum or a minimum. Similar at x2, we don't know whether it's a maximum or a minimum. What do we need to do? That is
We
where
need
the
to substitute.
need to do what?
Substitute.
Okay. So now we need to do again second partials. We need to differentiate again. This is where higher order comes in. We need to do again, differentiate again. Okay. Those derivatives that we had, these, you have to differentiate them. So this one is differentiated with respect to x1. At first, it was differentiated with respect to x1. We need to differentiate it again with respect to x1. It will be -6, right? Because this and this will become zeros. Are you following?
Yes.
And that other one, again, the one that was differentiated with respect to x2, you differentiate it for the second time. So these ones where there is x1 and where there is no variable, they become zeros, right? Then you have -10 as the second derivatives. Okay? Then what you need to do now from here, you need to do the cross partials, all right? The cross partials. You know what a cross partial means? Simply means that this same function. So first of all, differentiate x1 two times, the second time, also x2 for the second time. Get it? Right? Then number three, find the cross partials. Now the cross partial simply means this first, the first partial derivative was done with respect to x1. Now you need to do it with respect to x2. That's what cross partial means. So we're differentiating this with respect to x2. What will be the answer? It will be 2, right? Because this and this will become 0. I guess you're following. I say, when you do the cross partial for this one, cross partial simply means at first it was differentiated with respect to x1, yeah? Now you differentiate it with respect to x2. That's what cross partial means. So differentiating this function with respect to x2, this will be 0. Even this will be 0. Then you have 2, right? Because x2 differentiated at once, it will be negative. It will be just a 2. You got it? Also, this side, this one had been differentiated with respect to what? To x2, yeah? So now we need to differentiate it with respect to x1. It will become 2 as well. What you should learn is that the cross partials are always the same. Cross partials will always be the same. Yeah. So it's 2, 2. So let's go ahead. How do you show whether the function is a minimum or maximum? We haven't reached there.
Wait, kindly just go back a bit. I didn't try it. Wanted to just
Okay. We are slowly getting into economics, right?
Yes. I'm scared.
From just common calculation. You don't have to be scared. This is how the language is getting elevated. Yeah, macro can be very confusing. Yeah, if you don't know calculus, it can be very bad. Because I'll say, can you do cross partial? Then you'll be saying, what is cross partial?
So when we are told to do cross partial, you're supposed to first derive the two functions first, and then second, then the first derivatives, then you do a cross partial, right?
Yeah.
Okay.
You do on this first derivative. That's where the cross partials are done.
Okay.
Now, we want to know whether these functions, those points, the x1 and the x2, the function is what? Maximum or minimum. Now listen, if we use the ordinary way for optimization of a single function, we know that if the second derivative, like this one for x1, if it's less than 0, it means the function is what? It's maximum, right? Yeah. Now, unfortunately, the second order condition for multiple augment functions is not that simple. You don't just end there. Why? Because the sign of the second order direct partials only ensure an extremum in the, in the cross partials. So in short, you don't just end on finding the second derivatives. That's what we are trying to say. Okay. So what do you need to do? What do you need to do? You need a function. Okay. You need a determinant. You need to employ matrices. You need to you need to produce a Hessian determinant. Produce a Hessian determinant. A Hessian determinant is easy to form as long as you know how to deal with calculus. It is formed from those partials that you have done. So the first one will be function of 1, 1. The function of 1, 2, that's a cross partial. The function of 2, 1, that is a cross partial as well. And the function of 2, 2. I'll explain again so that you understand. A Hessian determinant is made up of the function of x, x, that is if you are doing with x, x, like the same function, that x1, x, x, then the function of x, at first you differentiated with x, now you differentiate it with y. That is a cross partial. You've seen it, right? Like the first time the function was differentiated with respect to x, then you had to differentiate it for the second time with respect to y. That is a cross partial. That answer right there. Then when you get here again, the function that you have differentiated with respect to 2, then you differentiate it with respect to, or x, what is this? With respect to y, then you differentiate it with respect to x2. And then this one is the function that you just differentiated with y, and you repeated differentiating it with y. You get what I mean, eh? That is the formation of a Hessian determinant. Please write up that. You have written that?
Oh, yeah, this one.
The Hessian determinant. Once you formulate the Hessian determinant, then you can easily evaluate it. All right? Now, the rule is, these are the rules. If the Hessian determinant is positive definite matrix, then at that point, the value of x is a local minimum. But if it is negative definite matrix, then it is a local maximum. I know you are not yet understanding what you mean by definite positive or definite negative. I'll explain in the next 1 or 2 minutes what we mean by that. So, let me finish it up so that you understand. But let's evaluate the Hessian determinant so that you understand what I mean. Okay. What was the F11 is what? -6.
-6.
F22 -10.
-10.
And the cross partials are just 2. The 2. You get it? Then you need the determinant. This one is a determinant on its own. It's a determinant of a 1-by-1 matrix. If a matrix is just made up of 1 digit, the same one will be the determinant. Those are rules of matrices. So this is the D1, the first determinant, 1. It is equal to what? -6, which is less than 0. Then from there, we'll have to do the second determinant. Now, the second determinant will be for a 2-by-2 matrix, which is found by doing what? You do the product of the major diagonal minus the product of the minor diagonal, isn't it? Product of the major diagonal, say -6 times -10.
Which is
That is
60.
2 times 2. So that is 60 minus 4, which will be 50 what? 56. It is positive. Okay. Now, at that point, listen carefully. If the function This is a key thing.
Mm-hmm.
If the function is positive definite, it means that all the determinants, D1, D2, D3. By D3, I mean the determinant of the 3 by 3 matrix. They
Mm-hmm.
are greater than 0. When all the determinants are positive, then you say the function is positive definite, yeah?
Mm-hmm.
And if the function is positive definite, do we have a minimum or a maximum?
Minimum.
Minimum.
Mm-hmm.
And then if the signs are alternating, okay, with odd numbers being positives, with odd numbers being positives, like negative, positive, negative, positive, like that. At that point, the function is a negative definite. So that simply means the first function is negative, then the next one is positive. Then the third one is like that. The reason why I'm explaining like this, when you come upwards in micro, somewhere the higher orders, you deal with complex matrices. They will not just be 2 by 2 matrices. You go up to maybe 4 by 4 matrix where you have 4 determinants. Determinant for a 1 by 1, determinant for a 2 by 2, determinant for a 3 by 3, and the one for 4 4. So that's why I'm trying to explain in advance.
Mm-hmm.
So this function is a definite what? It's a definite negative, a negative definite function, which means at that point you have a local what? Maximum. You get that
Maximum.
point?
Mm-hmm.
That is how you make a decision. Language has changed, eh?
Yes. Ish.
We are slowly changing. So now, what if none of the two are obeyed? For example, you find that D1, of course, I said D1, D2, if they are all positives, that is, they are all positive, that is positive definite, eh? If
Mm-hmm.
one is negative, greater than 0, negative, greater than 0, at that point, this is positive what?
Definitely.
Oh, this is negative definite, yeah. And if the signs are alternating like this, negative definite. What if you find a negative? Again, the second one becomes a negative, which means none of these rules has been obeyed, right?
Mm-hmm.
At that point, the function is neither positive definite or negative definite. So we say that a function is neither minimum or maximum. It has a saddle point. You say it has a saddle point, right?
Mm-hmm.
That is where saddle point comes from. This is what we were trying to say. A function has a saddle point. A saddle point looks like this. You've seen when you draw that function, it flattens just like a table. You understand? It's not
Mm-hmm.
curving like this or curving like this. That's what we mean by saddle.
Mm-hmm.
So the function is neither maximum nor minimum. It just saddles. It produces a saddle point. That is if none of these is properly obeyed. Any questions?
I'm
Are we
coming this
fine?
way. Yes, we are.
That was about unconstrained optimization. No limitations whatsoever.